All right, I'm picking up from Friday. Have your all screwed up out? Sean, let's go. All screwed up out. I need data. I need all your data. You should have done your R-squared value. You should have a sketch of a graph. I'm moving pretty quickly because I know that tomorrow I had some comments on the thermo extra credit, which was like, what would you change about APChem right now? So instead of doing a lab the day before break, I'll do a lab next week sometime because you guys said I'm learning from practice examples or I need more time in the lab. So I'm going to have a start of pre-lab today, but we won't do the lab until the following week. So, you guys ready? You have your data. All right, I have people that don't have their data out, but I think we're getting there. Okay, so you guys have the data, right? That data has to be used to give information about the kinetics or the rate of a reaction. And so that's one point to kind of maybe write down for yourself. A lot of times you will think like, oh, I can just look at the reaction go. Well, hydrogen gas is in a ratio of 2 to 1 with oxygen gas, and so the rate's going to be blah, blah, blah. Well, you can't do it from a reaction. You have to have data. So you'll see that this packet has graphical data, data charts, information you can plug into a calculator to kind of manipulate the data. So it's all data driven, right? So you can imagine that we have to collect data, hence our all screwed up lab. So Levi, we just basically screwed nuts on bolts. That's all we did on Friday. And we took notes, so you should watch the video. And we said hello to you. That was our welcome. But we collected data that way. And then also in the lab, you guys will be collecting data. And you guys told me you would use Beer's law, right? You said take a colored substance, look at the concentration, because that was like a colored, the depth of color kind of relates to the concentration of that species in the aqueous solution. So we're going to be collecting data a lot with colorimeters. What are colorimeters? They're not calorimeters. Colorimeters measure something with a cuvette, you tuck it in there, and then you measure the color depth, meaning the concentration. We'll use that. We'll also do some visual timing, like one time for 10 seconds a color or a species of color might be in the reaction, and then it all the way gets consumed. So what color is the reaction at this point? If the colored reagent is all the way consumed, what color is what color is the solution? Clear, right? So you can time when it's clear, and just take a timer and do it. So at this point in time, have we talked about time other than on the axis? Not really. Okay, but we will do a lot more today. So I want to hear from different groups their R squared value. So for round one, what was the R squared value for your graph? Let's go with, yeah, thank you. I just need some volunteers.
0.983.
0.983. Okay, I need another one. Yeah. 984. Vicky's got one up there. What else? 0.99. Ooh, 996. Girls rule. What else? 0.991. Oh, sorry. My bad. 0.9. Sorry, one. 0.991. I think I had 5 groups. Is there a 5th group here? Yeah. Avery. We need them sig figs. Okay, so 0.99. Okay, so this whole relationship, and I know that you guys have taken math, but I'm trying to do a better job of explaining like why this matters. Having a linear relationship is like the best thing ever in math, right? Because a linear relationship is like, it's very predictable. If it's a direct relationship, you go, okay, if the concentration goes up, the rate goes up. But how much? It goes up by the slope. The slope is a great predictor of how fast things go. Right, so if I have a linear relationship, I can really do a lot with predicting. If I have like an exponential relationship, or I don't know, those other relationships, they're just not as useful, and you have to do a little bit more math to kind of get to the end result. But linear relationships are absolutely wonderful. So obviously, pretty linear, right? Pretty linear. So what would you say? You did some reading on orders, but what is directly related here through this correlation? What were we measuring? What's your data say? You are putting that together right now, but go back to what you actually collected. What data did you actually collect? You said time it took to... Okay, so that's the time it took. But what was your other axes? Okay, so you really were only... These are the number of screws that were on... Okay, so what was that called though? It was called something.
Number of loose screws.
Loose screws, okay, so number of loose, I was like, what was it called on the graph? Okay, so the number of loose screws versus time. So you actually measured the change in concentration of the loose screws, right? So over time, what happened to the number of loose screws? They went down. Okay, so as the number of loose screws went down, the time was it just pretty regular, like it took 2 seconds, 2 seconds, 2 seconds, 3 seconds, 2 seconds. It was pretty regular, right? So if I had to graph it, which you guys did, you should have a pretty standard slope or a constant slope. Kind of like that. Was that kind of what your first graph looked like? I said directly related. I meant linear related. This is not actually 100% direct, but this is a linear relationship at an R squared value of approximating, not direct. It's like 0.99. Okay, so most of us did a pretty good job there. That's R squared. Okay, so as the loose screws went down, did it change your rate? Hold on. Let's try that again. Rate is change over time, right? Change in loose screws over time. Do you see the slope stays same, 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 same? Okay, you should probably be writing some of this down because this is called a zero order reaction. Okay, this is called zero order because does it matter if you had 1,000,000 screws or like 1 screw in your bag? Did it affect how fast you could put the screw on the nut or the nut on the screw? No, because you were grabbing for the nuts and bolts at the same time, you put them together, boom, you were done. So this is zero order because the slope is constant, meaning, and slope in this case, the slope does matter because the slope is representing the number of screws over time, right? The y-axis over the x-axis. So if the slope is constant over time, does the, let me actually go to the next page, does the number of screws affect the rate of reaction? No. So, remember we're talking about rates of reaction, right? We're talking about how the reactants react to make a product. Nobody really cares about the product per se, because like they don't control our rate of reaction. It's the reactant's job to like collide and do some damage, right? So if the number of screws don't matter, the order of reaction is called zero because they have zero influence over the rate of reaction. But if your reactants do have influence over your rate of reaction, we call those first order, second order, third order, and so forth. But if they have zero influence over the rate of reaction, we call it zero order. So because there was no choice in like selecting, we had that one nut that fit on the screw. There was no like small ones or the 2 big ones that you guys experienced in round 2. That's going to be caused, that no choice situation means that the rate is determined by how quickly you can thread that on there, but not the reactants, right? You weren't considering yourself a reactant. So you guys were like, oh, Emma's the rate limiting step or the rate determining step because maybe she took 5 seconds versus Allie's 4.99 seconds. I don't know. So you had some things you guys that were influenced the rate, but you weren't reactants. The screws were reactants. Okay, so if you have if your reactants play zero role in the rate of reaction, you call that zero order. So we're going to talk about orders a lot more from data today. But it has to be a linear fit, meaning a linear relationship of concentration versus time. So the concentration for us, we weren't measuring like solution concentrations. We're actually counting screws. This is like basically concentration versus time. So this is a memorized relationship. If the relationship between concentration and time is a linear fit, it is called zero order. We're going to change that up kind of as we go. But these are some of your answers. Make sure you're documenting some of this because I think that you guys have had a number of questions to answer, but then you need to kind of adjust as needed. So does that first relationship make sense? AJ, why is it zero order? Tell me one more time. Don't say it directly the way I said it.
Because the slope of the constant slope of the concentration is changing at exactly over time.
Okay, so the concentration is changing the same rate over time, meaning the rate is constant. So it doesn't matter if I change my concentration, the rate is still the same. Okay, give me a thumbs up if that theoretically makes sense right now. Okay. So the next one, what kind of data did you guys find? So round 2, the number of correct screws, or am I calling this wrong? No, nuts, yeah. So as you guys, you saw me add your extra 10 nuts, right? You added those, you mixed them up, what happened to your rate over time? So tell me your R squared values. Let's do that first. Yeah, Jacob. 0.97. Can I get another?
0.97.
Okay. What else? Thanks. I'm hoping for some really crappy R squared. 0.39. 0.974. Okay.
0.976.
And how did you guys graph this as concentrate or number of loose screws versus time, right? All right. I'm really actually excited about this. Very, very excited. Because as you guys probably realized, what happened to the number of correct screws over time? They what? They decreased because they were used up, right? So the number of correct screws over time in that bag with the other 10 that were the incorrect ones, you were rifling around, wrong one, and put it back. So over time, what should have happened? Maybe not for everybody because somehow you guys are magical and have the correct screw in the first time. I'm not sure. What should have happened over time? So are you saying the reaction took longer or shorter? The reaction took longer, so the combination took longer. So as you had a lot of the correct screws, so 10 or so of the correct screws, it was pretty fast. But as you went down to 5 of the correct screws, the slope got kind of, you took a long time, right? So it kind of leveled out. And as you got down to like 1 of the correct screw, good Lord, it took you guys like 10 minutes now. I didn't do that, but it took you a while, right? So what should this look like? Sorry, that is exponential. Exponential decay. So is that an R squared of 1? It should be like an R squared of, I don't know, 0.5 even, 0.4, something pretty low. But it does depend on your data, right? Everything is data driven. You can't judge your data. Therefore, I can't really judge you for your 0.97s. But what you should at least see is that the first one was like really, really good, 0.99, 0.998. Very, very linear with concentration versus time. Would you say this is linear with concentration versus time? No. So tell me why. Good Lord. Or ask me the question first.
I just want to say, our like error, I guess, for getting the higher R value comes from like determining which screws will fit, and since you can see which screw you're picking up, like you knew which ones weren't going to fit when looking at them.
So they had their Hawkeyes on the reactants?
Yeah.
Okay, so they had an extra variable called Hawkeye, watching, where those roots come back in the bag and kind of used that as a control variable that we didn't, a constant mix in the experiment where we didn't look at it.
Inconsistent rates, like, throughout.
So he's basically saying they cheated. It's okay.
Yeah.
Okay. So, but if we had, we should have had a pretty lengthening time of rate, right? Can I take your question? Or do you going to answer my question? Okay, so my question, make sure with me, this is the reasoning behind this. Over time, our rate got slower, right? The time got longer. The time to change the concentration extended. Why? Well, so that is true, but that's not the first connection. That's like later on the assumption you're making. Tell me specifically why the rate got longer.
It's because the concentration of our reactants got lower.
Okay, so over time the concentration of our reactants got lower, so the rate or the time extended, right? Okay, so that's important. That's the inverse relationship we see here. But what you're saying, and this is what I think you're saying the change in concentration influenced the rate, right? Okay, so is there influence or zero influence on the rate? There is influence, and I'm going to go ahead and tell you that this one in particular is first order, and I'll tell you why as we look at data later. But if the concentration of the reactants do play a role, like they do influence the rate of reaction, they have to be important, right? So if you're important, I didn't do the rest of this with you guys. If they're important, that they are part of the rate law. It's something called a rate law, and we'll be talking about rate laws today. But in this case, I think it's on the next page. There we go. You should realize that the rate got slower over time, so the number of correct nut did influence the rate, and so we can't just look at our graphical relationship and go, oh well, here's the relationship, concentration versus time, because that doesn't match anymore, right? That's not linear. There must be a modified version of this that makes it linear. I'll tell you the modified version is ln. If you did the ln, the natural log of the concentrations over time, it would be linear. But we're going to do that tomorrow. So we can't verify the order based on the graphical analysis. We have to think outside the box, which is why I'm telling you there's manipulations to data like natural log, 1 over concentration. We can manipulate it in many mathematical relationships. But first order kinetics was where the concentration plays a role in the rate of reaction. There's also second order kinetics, which we'll talk about here in a second. So let me go back and make sure I told you everything I want to tell you on the first one. Oh, do you guys have your slopes written down? I didn't ask for that. Do you guys have your slopes written down from this first trial? You could probably quickly find it, but tell me what would your slope represent for that first trial? Say again? So I heard rate too. Right? So the slope is change in concentration over change in time, right? Which is the rate. So how would you tell who has the fastest rate? Okay, greatest change in smallest time. So when you say greatest, are you talking about how it's highest magnitude or the highest number? Because remember, this is negative slope. Highest magnitude, right? The greatest change per time, meaning absolute value of magnitude. And I'm just emphasizing that because the explanations on thermo, like biggest delta H, like does that mean endothermic or exothermic? When you say biggest delta H, that means endothermic, right? It's like the largest value. You gotta say greatest exothermic or largest exothermic value. We'll have to work on the vocabulary. Okay. So whoever has the largest magnitude of slope would have the fastest reaction. And then, okay, I think we're good. So here's the last part I want you guys to write down on your paper. And here's how we write rate laws, and I'm going to show you this now, but we're going to do some examples with this in a bit. Rate law for number 1, and rate laws are always written in this format. Rate is equal to, did you guys see something with K, like a rate law constant K? Yes, sorry, my computer's being funky. So this is what we would write. K times concentration of, I'll get that in a second, screw to the what power. If we said number 1, what was the order of number 1? 0, which is 0 power. So we would write screws to the 0 power, so that would just be rate is equal to K. K is a constant. We're going to talk about what that constant means in a second. Okay, if rate is equal to K, what are the units of K if you know what rate should be? Yeah. So I'm just going to say concentration. What's our normal concentration unit? Molarity per second. Okay, the units of K in this case match the rate units because rate is changing concentration over time, which is seconds in this case. Okay, so what would be the rate law for reaction 2? Rate is equal to K times concentration of screws to the first power. Okay, this is concentration of screws, which we're going to call molarity. I know that's not a solution, but solution of screws, okay? Molarity, so what would the units for K be? Say again? You say moles per liter. But we already have 1 mole, right? Molar. All right, here, let's backtrack. What's the units for rate, always, in this case? Molarity per second. Okay, so I want molarity per second equal K's units and screws units. Well, what's screws units? Concentration, right, which is molarity. Okay, so how do I get this molarity and blank these units here to equal what's left over here? What does K have to be? Per second, or 1 over second, right? K's units change every single problem because the rate law constant, this K constant that we're going to talk about a bit more today, they have to make the order of reaction agree with the rate overall units. Well, the rate overall units, they will always be change over time. Change of concentration over change in time. Change of concentration over change in time. The order will influence how often molarity is used actually in our rate law, but the K has to make them agree. So they're the middleman. They have to make sure the units agree. So we'll be writing units a bit here. Okay. So this reaction was, what was it? I said screw, yeah. So nut plus screw equals, I'm just going to say volt. So which of these reactants mattered the most? Which ones did we track? We tracked the screws, right? So that's why we included screw in our rate law. We didn't include the nut because we don't have data for the nut, but we could have done that. We could have figured out the order of the nut as well. But we didn't because we didn't track that. Yeah.
And like the lab setting, will we be told like what we should keep track of or like?
Yes. And sometimes we assume things change so minimally it's basically constant. If it's constant, we don't write in our rate law. Like one of our reactions we'll do later, we're flooding the system with so much sodium hydroxide. Its concentration is changing like this much. It's not even measurable. So, all right. So let's talk about rate laws a little bit more. And that's where you guys have some in your notebook or in your packets. We're going to kind of go through this together. I want to show you some of this stuff now. We'll practice together. So what you'll see is the vocabulary. It differs. So I'll just say rate law. But what I mean is differential rate law. Well, differential sounds like derivatives. Okay? It's definitely related to calculus. We're not getting into the calculus nature. Maybe just a teeny bit tomorrow to talk about integrals. But there's something called differential rate laws, which we're talking about today, and integrated rate laws, which we're talking about integrals. I will show you the proof behind it, but I will not expect you to map out the proof, because the proof is about 17 steps or so. But I will just show you that it's related to calculus, and that's it. So if we're talking about rate laws, we're talking about differential rate laws. They are listed just like we write there. Rate is equal to K, which is the rate law constant, it's a lowercase k, times reactants. And so I think right now you're like, well, duh, it's reactants. We're talking about order. We're talking about forcing a reaction to occur. The reactants control the formation of products. Later on, when we talk about equilibrium, we're going to start talking about reactants and products together. So you're going to be like, hold on, rate laws, do those have products or reactants? Please put big and bad on your paper. Reactants, expression that shows how concentration of reactants change over time, or how reactants control the rate law. Okay, and in this case, we're specifying that some reactants, they have much more influence over the rate of reaction, whereas other reactants don't. But you can't just assume that. You can't just know that. You have to have data to prove that one reactant might be controlling the rate more than the other reactant. And that's because, and this is I think what Alan was getting to earlier, guys, we don't even know how many steps some of these reactions take, right? They might take one step and be done, like A plus B yields AB. Or there might be 15 steps in the middle that we don't know about, so we can't always take it for face value. We have to know more about the reaction mechanism, which we'll get into a little bit more tomorrow. So we have to know about the reactants and the formation of products, which we can track either one. We can track consumption of reactants or formation of products. So this is the generic format for a rate law, which I just kind of wrote on the other slide. But I want you to know the vocabulary behind this. The K, my smart board is not being smart today, guys. Okay, the K is called this is the small k, it's called the rate law constant, and its units change based on the order of the overall rate law. That is modified occasionally. It is temperature dependent. So let's just say, for clarity's sake, Alvin's group, who's in your group? A couple of you guys here. Okay, maybe you guys are at like negative 30 degrees Celsius doing your lab. You're like, cold. Screw it, okay, my fingers are frozen. Okay, so you'd have moved a lot slower, right? Because hopefully frozen fingers don't work well. And then say Allie's group, they were at, I don't know, 100 degrees Celsius, but they weren't burning, right? They were just like moving really, really fast. Like molecules do move faster in hot temperatures, right? Molecules move slower in cold temperatures. That's related to the temperatures related to average kinetic energy, right? Which we could represent on a Maxwell-Boltzmann curve. I skipped that last week, but I'm gonna pull it back up for you. So how does that temperature relationship, how does that get embedded in the rate law? It gets embedded in the K value. So if you don't have anything else to compare and you're like, okay, I know K for this reaction, I know K for this reaction, and everything else is the same. You can look at the K values and you can figure out who's who's at a higher temperature based on the constants. Higher constant generally means hotter temperatures, yes.
Those brackets, absolute values.
No, those brackets mean concentration. Yes, so good point, and I assume that you guys know bracket means concentration. Who remembers that from honors chem? Okay, a couple of us, and we've used it a little bit. So the brackets are molarity. So we're taking the concentration of reactant A, the concentration of reactant B. We're looking at how they influence the rate, and these X and Y are orders. The orders can be 0, first, or second. We really don't go too much further. They have to be experimentally determined because we have to have data to support our thoughts here. Because we, like I said, we don't have all the details all the time. We have to look at the experiments. The one thing to note is that these are not the coefficients. So if I put a 1 here and a 1 here, and you're like, oh yeah, X and Y, they're just 1 and 1. They're all first order. That is an incorrect assumption. It could be true, but it's an incorrect assumption. The molecularity, which is what we term the coefficients, or the stoichiometric relationships between them, the molecularity of the reaction itself cannot determine the orders of reaction. You cannot just go straight from there. It's only if it's an elementary reaction can you do that. Yeah.
What is that unit change?
Unit change based on order. Depends on what order of our reactions up here. Okay, so that's what this last step down here says. Rate laws are not determined by molecularity. Okay, so give you guys a second there. We're still writing. These are just some things to know about rate laws. So there's a couple ways to find the rate law. Like I said, differential rate laws, the one we're focusing on today. Integrated rate law is what we're dealing with tomorrow. Differential rate law is very similar to what we've been setting up with concentration versus time, so you should at least make this relationship. Differential rate law measures concentration versus time. Versus rate. Time's going to come in here in a second. We had graphed concentration versus time because those were the variables that we could actually measure. But you can also represent it in another way, which I'll show you. This is some of the background knowledge I think is very important to understand kinetics on an elemental level. I don't have a graph right here. Hold on. I'll just graph one. Alright, so you guys tell me your thoughts. Tell me how you think rate and concentration are generally related. Does concentration control the rate, or does rate control the concentration of the reactants? Okay, so concentration's going on the x-axis, rate's going on the y-axis. As concentration changes, let's say this is talking about concentration of reactants. Let's say the concentration of reactants start here. The rate's going to be pretty fast, right? Got a lot of reactants. So, I'm sorry, this is concentration, this is low. Let me start off low. Well, now let's do concentration of, no, I'll start with this. Basically, as the concentration goes down, what should happen to the rate? Because there's less collisions, right? We call that the collision theory. So there's a relationship we can make through graphical analysis or through table. The table logic is where I'll show you guys first. So I'll hold off and I'll have us actually analyze our own graphs. I'll have another worksheet for that in a second. So the concentration versus rate is differential, but if I include time, that's integrated. Do you guys know that whenever you guys are working with integrals in calculus, it's integrated with time? Sometimes it's like a integrated, like as x approaches infinity, and then there's time involved. Okay, never mind. So it is integrated as related to time, and that's what a lot of us are going to be more familiar with. So, and then this is what I mentioned last week, but as this, you guys just came to this conclusion, as the reactant's concentration changes, that does influence the rate, right? It gets slower, there's less collisions. So instead of going, okay, calculate the rate of reaction, you're like, but where? But what time? We always agree that we start with the initial rate of reaction, because as things change, the rate changes, and then we're all talking about different ideas. We're talking about different parts of the reaction. So we always start with talking about the initial rates of reaction, because that's the one point that everybody can agree to. We can measure that one point, and we all can have the same data to work with. So everything gets a little bit messy when you start going through the reaction a bit more. So just to make sure you can read this rate law, you can see my exponents up there on the rate law. Did I print this part for you? I did, okay. I was like, I think it's like, what page is it, Emma? Page, is it, I labeled the pages this time. Is it, okay, so what's the number at the top of the page? 2. Oh, it is 2? Oh, I didn't label the first page, no bad. Okay, so on page 2, you have this fantastic redox reaction. You can see the rate law. So with respect to this guy, CR4, 1 minus, what is the order? There's an imaginary 1 there, right? So that's a 1. What's the order with respect to H plus? 1, because there's a 1 there. What's the order with respect to HSO3, 1 minus? 2. Okay, so we will call this first order with respect to HCrO4, 1 minus. First order here, second order here, but overall, summative, those orders are fourth order overall. So that's how you speak the language when you talk about orders. So here's the relationship. If something is first order, if I double the concentration of that reactant, it exactly mimics, that's exactly mirrored in the rate. So in first order reactions, whatever happens to the reactant happens to the rate. They're directly related. So directly related to rate of reaction. So if I double H plus, if I take the concentration of H plus and I times it by 2, the rate will also double or be multiplied by 2. That's because this H plus concentration, what power is that raised to? To the first power, right? Okay, so 2 to the first power is 2. And so if the rate's going to be mimicking that, if all you have to do is look at how the manipulated variable is, or how the concentration is manipulated, you raise it to the same power that its own concentration is raised to, and that's how the rate should be influenced as well, because that's the math behind it. That's how it works. And so that's just something called first order, directly related to rate. Can I move past that? Okay. So HSO3 bisulfite. If that's second order, if I take the concentration of HSO3 bisulfite and I multiply it by 2, it's raised to the what power? Say again? So, but this is raised to the second power, right? So the rate will quadruple, right? Because 2 to the second power is 4. So what you can see is that these are all reactants of a reaction, right? But which one is kind of more influential over the rate? Who causes bigger changes in the rate? The one with the higher order, right? So in this case, yeah, double H, if I double the hydrogen ion concentration, it doubles the rate, right? That's very predictable. But if I double the HSO3, who would have thunk that it would have quadrupled the rate of reaction? You're just like, well, it's just a reactant, right? But some of these reactants, when they react, there's different mechanisms they're used, or different steps in a mechanism they're used in, and sometimes they're more influential over the rate. In this case, if I double this concentration, it just so happens to quadruple the rate because of the relationship it has with the kinetics of the reaction. Yeah?
So if you like double both at the same time, like how would that?
That would octuple it. It would be multiplied together because everything's multiplied together up here, right? So that's a good point to make. If I change both of their concentrations, it's going to do whatever they do multiplied together to affect the rate, because everything up here is multiplied together to equal the rate. Good point. Have I lost anybody? Yeah.
What about zero order?
So zero order, since we talked earlier about this, zero order reactants have no influence over the rate. That means they're there because a step in the mechanism needs it, but it doesn't really control the rate of reaction. It's there. If it wasn't there, it wouldn't either. It's probably because it's catalyzed. Catalyzed reactions a lot of them are zero order reactions. Okay, so so this is just another case. If something were third order and I double the reaction, and doubling the concentration to the third order, what's 2 to the third? Okay, just really hoping no one said 6. Okay, what's 3 to the third? 27. No one said 9. Okay, we're doing great, guys. We're doing great. We are mathematically sane. Okay, so these are how those different rates look under different orders. So if something's to the first order, you'll generally just see A, or whatever the reactant is to the first order. Zero order, we can put the 0 there Or we can just write it like this, and that's what we wrote earlier for our trial 1 with the screws. We put the screws to 0 power, but we can also just take screws out of the equation entirely. And sometimes when you get a little bit more complicated, you have something that's first order and second order, you'll see it with 2 different exponents, but the overall is a summative nature of the orders to make the overall order of reaction. So I should give you some more examples of how those look. Yeah.
For the zero order, why isn't the rate equal to the like concentration? Because it's zero, or it's to the 0 power.
Because rate has to be represented as change in time, right? Somebody trying to get in there?
Yeah.
Yeah, I guess.
What's the password? Yeah, grab one from that. Grab one from the shelf over here. It's just not. There's a scale on the by the paper towels. Okay, guys, we're moving on. Okay, so nope. Actually, come back one more over here. Find a little stuffed animals there. All right, guys, you with me? This is me giving you one more chance to see how K, the little K rate law constant, fits the equations together. So if rate is, thank you, if rate is molarity per second, how does second order get represented? How does second order get represented? So this is squared, right? Second order would be a squared. So then how does K, units, get represented?
Oh, 1/2.
1/2 times molarity. Right, write down what you need to do. Because I'm reading right now. Sorry. Nope, sorry. Welcome back. Thank you. I literally hate when people interrupt me in chemistry. It's my biggest pet peeve. Okay, so yes, this is rate, which is molarity per second. This is K, which is something, and then molarity squared is what our concentration should be if it were to be second order. So molarity squared, meaning molarity, one of the molarities stay with us, one of them gets canceled out, so there has to be a molarity in the bottom to cancel, and then the second doesn't just randomly appear, it appears because it's in the denominator of the K value. So that can be written as K units as molarity to the -1 second to the -1, or you can split the molarity units as what? How would I write 1/molarity seconds with liters and moles separate? Liters where? On the top. And then I'll have moles seconds here. Or that can be written as liters, moles to the -1, seconds to the -1. That's about all I can do there. So you'll see these represented in different ways. I just want you to be familiar that these are all the same thing. Give me a thumbs up if those units all make sense. Let me just grasp this. All right, so we're going to be working through these a lot. The one thing that just about the commonality of how often you can see these, zero order is very uncommon. It does usually do with the catalyst because something's got to help the reaction, right? If the reactant concentration doesn't matter, usually a catalyst does. But a catalyst is not a reactant. Is a catalyst consumed? Not at all. So it's not truly a reactant. It's just a matchmaker, right, to bring things together. First order is very, very common. We will talk about half-life with this, like half-life of a radioactive decay. And then second order is generally with gas phases because it helps with recognizing that as you increase the concentration of gas phase, they're colliding very, very quickly, right, because they're high kinetic energy. It does influence the rate much more. All right, so this is called table logic. Is this in your notes? In the packet, right? Okay. I gave my packet to Levi, so I hope you're looking at that because I don't have it in front of me. So experimentally determined means that you have to have data from an experiment. Here's our first experiment. Over time, Levi did 5 trials of a reaction. And he measured the concentration of A through each of the trials, the concentration of B through all the trials, and he saw the rate it was different over time. And remember, this is initial rate because you have to do at the very, like, you add reactant A, add reactant B, measure the rate of change over the first 5 seconds, and you're done. You can't measure it like 2 minutes down the lane because the rate has totally changed from what it was initially. So the way you compare trials is that you have to find one trial that's and you have to find trials where you have one constant and one variable that's changed, right? So in this case, I'm choosing trial 1 and 2. So you got 1 and 2, where B's concentration is staying the same. So is B really going to be influencing the change in rate at this point? No, because I mean, it's going to have an order. We'll assign an order to it, but it's not the variable I'm changing to see how it influences the rate. I am changing A's concentration, but what am I doing to A's concentration from trial 1 to trial 2? What am I doing to the concentration? I am doubling it. Don't say adding 0.1. None of this is an addition or subtraction relationship. Everything is a multiplication relationship because it's a rate is equal to things multiplied together, right? So if I'm doubling A, how does that influence the rate? It is also being doubled. So from that mathematical relationship, you can say A to some power being doubled causes the rate to be doubled. So what is that power? 1. So what have you just discovered? A is with respect to first order, or A is first order. Based off data. Got it? All right, so we chose B to be constant for this particular instance. Let's go ahead and choose another constant. You guys tell me what you guys want to do. Trials what and what? 3 and 4, okay. So trials 3 and 4 stay constant right here for A. So we already know A is first order. Let's just ignore that for a moment though. What's happening to B over these over these trials? It's doubling, okay. What's happening to the rate? It's quadrupling, so B has to be second order to allow this mathematics to work out. Did I move too fast? This is called table logic. I love table logic. It's just like, look at the table, look for the trials that are constant, one variable changing, look for the relationship between that concentration change and rate. Choose 2 other trials, keep one constant, it has to be the other one, don't choose the same one. Look at the relationship between concentration change and rate. Remember, this is differential rate loss, we're looking at concentration versus rate. So if this is second order, one second, I'll get your question in a second. What we would need to do then is write this rate law. How would you write this rate law? How do you write a rate law? Let me ask that first. Rate is equal to, okay, K times concentration of A to the first power and concentration of B to the second power. Okay, now let's solve for K, because it says in the value of K with units. Richie, can I get your question in a second? Or is it relevant right now? Okay, cool. All right, so here's how we solve for K. You guys should be writing these examples down with me. I feel like I'm just talking to the wind. If I have rate, I have to solve for K. What is the value? How do I rearrange this to solve for K? Rate is over what? Concentration of A to the first power times B to the second, okay? So if that's my general format for finding K, you choose one trial, because all of these trials, they're talking about the same reaction, right? Assuming this person was diligent and collected good data, the K value will be the same for every single trial because it's the same reaction. So the K is representing the slope of a graph. I'll talk about that in a second, but I'm just going to choose trial 1. Let's plug this value in. Okay, so 0.2 is the rate, 0.1 and 0.1. So the rate is in right your units, 0.20 what? What's the rate units? Molarity per second. Over, what's A's? A was for trial 1, 1 or 0.10 molar. B was 0.10 molar squared. Okay, so this is going to help you see the units of K come to life. What units cancel? One of the molarities, and then seconds are in the denominator of the numerator, so really they're just in the denominator in general, right? So what's let's see, this is 0.1 times 0.01, 0.001. So 0.1 is still there, so I'm just doing, let's do this mentally. Let's stretch our brain. Get ready to stretch. 0.2 over 0.1, and this is 0.1 squared, right? So that's 0.01, correct? What's 0.01 times 0.1? 0.001. So then that's what? One. You guys are, it's 200, right? I can so much better do scientific notation. That is 2 times 10 to the negative 1, right? This is 1 times 10 to the negative 3. Okay, so 2 over 1 is 2. 10 to the first minus a negative 3. So that's adding, right? So what is that? A positive 2? Okay, can you do this in your head better? Yeah. I can totally, that's what I have to do to make sure I can mentally math it up here. So this is 200 where's the units? Say again? 1 over molarity squared seconds. Because that squared is still there, right? Alright, the unit's okay. You ready? Let's do another one? Yeah.
So where did you get the 0.1 from?
I pulled it straight from it. I did trial 1. I just looked at the data here, and I pulled it down. So whenever, use the data from one trial and substitute into the rate law that you just made, and then find your k-value. Yeah. Yes, you're squaring the entire thing, which happens to be molarity as well. Good point. All right, let's do another one like that. Maybe not exactly the same. You guys go ahead and do that one for me. This is on your packet.
Well, the first one was on the NXMF packet.
Oh, good. Okay.
It's also on your
Well, you guys just do it for now. Just go ahead. You got it. You got it. Yeah. The K is just a constant. If you're good to move to example 4, you can, but I'm going to go through example 3 first. All right, Kurt, all you, man, tell me your thought process here for the class, quickly.
For the first one, for finding A,
okay.
in trials 1 and 2.
Okay.
So A doubled
while
B was constant.
Okay, so B was our constant, trial 1 and 2. A doubled, what happened to rate?
It was also constant.
Okay. So what can you tell me about A?
It's a 0 order.
Right, if A doubles and the rate doesn't change, it's not controlling the rate. So A is 0 order. Okay. Tell me your next step.
I haven't finished it yet.
Okay, well let's do this part together then. Go for it.
So you use trials 1 and 3.
Okay, 1 and 3 here. That's constant, right?
Yeah, A is constant.
B is
doubled.
Okay, what happens to rate?
I was trying to divide that to make it.
You can do this. 7 to 28. Right? It's basically 7 to 28, right?
Got it.
What? Quadrupled, right? So 7 times 2 is 14. That's not going to work. 7 times 4 is 28. But that is, if you did take 2.8 times 10 to the negative 4th divided by 7.0 times 10 to the negative 5th, it would be 4. And you definitely should do that if you're not able to see that relationship. Don't let that get in the way. So B is doubled, but it quadruples the rate. So what's the order? Second order. Okay, a little not means order as well. So then what's the rate law?
Rate equals
K A to the 0, and that's just showing the order. You don't have to show that. And B squared, okay? I'll tell you the thing that everybody ever usually messes up on later on in life is that we miss on that K. We just go straight to the concentrations, yeah.
And like for your response questions, do they want us to have like negative 0?
No, that's good. They'll take either for that one. You could just write k times b squared. Yep. All right, so then I'm going to show you the ugly algebra method. This is the way that I like to call it. So the first type is, this is table logic. We did this through table logic. I'm going to show you the same system through ugly algebra method, so that sometimes you don't have something that's so pretty, where it's like, oh, I doubled it and it quadrupled. Sometimes it's like numbers that don't mathematically really make sense through multiples. So here's your method of doing that. If you're doing it by ugly algebra method, you have to show, and I won't show you with the logs right now, you have to say, okay, experiment 3 over experiment 1 is equal to k, and so you're taking your two experiments or trials, and you're writing out the rate law as they apply. So I'm going to say, we just figured out a to be 0, or we just figured out a to be 0 power. This k is not above the equals mark, it's here. K, a to the 0, which is 1, so I'm actually going to cancel that out. B to the x. Let's say we're trying to find what that power is. Maybe our math didn't work out so beautifully up here. So what you're doing is, if you find one pretty easily and you can't really find the other one, this is called ugly algebra method. So I'm comparing rate 3 to rate 1. So this constant, it's a constant in all trials, right? So it can cancel. A is 0 power, right? We'd already determined that, so it doesn't influence our rate at all, so I'm canceling that out. This is mathematically how you show your work for a free response. Because, like, this up here makes nonsense to an AP reader, right? You're like, oh, she did, or he did. But if you can try to make some sort of linear work scheme, this is my best bet for that. You'll get your credit. So at this point, I'm going to plug in my B values from rate 3 and 1, and my rate values from 3 and 1. Can you guys tell me? Well, here, I'll just show you here. So this is 0.2, right? Molar per second. What was the rate for rate 1? It's on your paper. Oh, sorry. 0.28. Here's your rate over here. 2.8 times 10 to the negative 4th molar per second. What was your one for? It was the same, right? Okay. 7.0 times 10 to the negative 5th molar per second. That's equal to, we canceled our k's out already because they're constants. We canceled our a's because they are just the first, or they're 1. My B concentration for the third trial is 0.2, right? What was my B for the first trial? I don't have it on. What is it? 0.1, okay. Do you guys see where I'm pulling this data from? I'm looking at first and third trial, okay. And this is to the x power. So I know you could go, oh, well, how can I simplify? Well, what's 2.8 blah, blah, blah divided by 7? Okay, that's 4. Now, this is a simple example because it's working with data that works out really well. So 4 is equal to, combine these, what's 0.2 over 0.1? Okay, that's 2. Don't the similarities cancel here and here? Right? So that's 2 to the x power, because the x, when you combine the fractions, the x does apply to both. So you could easily then say x is equal to 2. But how can you prove this with math? Log. Okay, how do you log this? What happens when you log this? Log of 4 is equal to log of 2 to the x. Okay, I'll help you. Then what do you do with the x? How do you pull the x? Or what's the rule? It can go in front of the log. You guys remember this? X goes in the front of the log? Do you guys remember this? Oh my gosh, you guys are slackers. Okay, x, this is like the fun part where I can actually do hard math. Okay, this isn't hard math. I can do math, like real math, not just algebra. Okay, so I miss math just a little bit sometimes. So then you get here, and then what do you do to isolate x? You just divide by log of 2, right? Divide by log of 2. And then this cancels. Log of 4 over 2 is 2, x is equal to 2. Now, I know you could easily do that from here, or even from above, but I wanted to show you with an easy example that you have a backup plan. Plan B, if you need to. This is called ugly algebra method. Got it? So I'm going to leave that there for a second if you need it. Does anybody remember their log rules now? A couple of them? Okay, you guys do 4 for me. This is on your paper. Do 4. And do example 5. Example 4 and 5. talk to each other as well.
Smaller shoes. Yeah, you double.
Oh, that's fun. Fun realization.
Well, yeah, well, we don't care about that.
I know that. What?
It's actually, it's usually easy because of your teacher to say that. Because all you do is click on it.
What are you talking about?
Focus, my children. Focus.
So is it?
Yeah. What?
So what's the order for NL? It's true, it's touchy.
No, no.
Alright, what did you get one more time?
So that's what the or does.
I don't know, I wouldn't listen to that. What is it, rating with NL is W for 21? Yeah.
I'm talking about
Alright, raise your hand if you're done with example 4. 1, 5, okay.
Come on, Sean. Yes. Oh.
So how does
Yeah, it's 0.05.
wait, I don't know. What's 1.5 times 2? Yeah, what's 3 times 2? There you go. Don't worry about it.
All right, eyes up here, eyes up here. I just want to make sure we're on the right track. So part A, you guys got rate is equal to K times H2 to the first and O to the second. Thumbs up. Thank you. Plug in your rate, plug your variables into your rate law constant. Mathematically, can you mentally approximate this? Let's work on that because I know that's still the struggle. What is 5 to the second power? So 25, right? So then what's this? 0.025? Well, no, the 2 gets bigger, so it.
But it's
Is the 5 is
we just had our
So is it 0.0 or 0.00?
Oh, we had an argument.
So did we double check that on our calculator?
Yeah.
Okay, thank you.
That's what we had to do.
Okay. Oh, sorry. This molarity squared. Okay, so I was like,
0.050 times 0.5.
say again?
0.050 times 0.5.
Yes. 0.5 times 0.5 is 0.025, and then 00 is.
0.05 times 0.05.
Yes,
Yeah, because in order to do 0.025, we have to multiply that by 0.5 instead of 0.05.
I have no idea what
I gotta
we're
wait.
talking about anymore. So, all right, this is not the most important piece. This is just a small portion of this problem. Yeah. Like I know this is right. I'm ready to like actually calculate. So, love you, but we have still a couple more problems to do. Okay, so then this times this is 2 more zeros, right? Okay, so 2 more zeros. I'm just playing with your math game, okay? So this is cubed, right? Okay, because that's molarity times molarity squared. And then so what units are going to cancel? 2 of the molarities, leaving us with 1 molar on top, and the second stays on the bottom. So we're good. Rate's going to be molar per second. That's what rate should be. So then what's 6 times 10 to the negative 4th times this? Like, that is a. What is this? It's 1 point. Sorry, it's 1.5. Your 7 zeros is right, but I'm putting in scientific notation. So 1.5 times 10 to the negative 8. I constantly say meters per second, molarity per second. Molarity per second. All right, that's our rate. All right, so then what would happen if NO is doubled? First off, what's going to happen if NO doubles? What's going to happen to the rate? It's going to quadruple because it's a 2 squared, or 2 squared. And then if this is left unchanged, meaning nothing happens, so what should happen to our rate? Just simply quadruple. So then what is that quadruple? 6. So 1.5 is 6 times 10 to the negative 8 molar per second. Whew, okay, let's do that. Hopefully you guys have started the last one. Here, last one. Maybe I can just have somebody talk me through it. Who feels good from the back? Thank you, let's go. Ready. Start me off, man. Well, no, hold on. Give me baby steps. I want from the beginning. No. Start me off on how you got your rate.
Well, I got rate in order. I think the order is right.
That's where I want you to start. Tell me how you baby steps. Very, very beginning.
So, I think it's Cal 1 and 2.
Okay.
The order for the bromide.
Okay.
And since the bromide doubles it, and the rate doubles, the rate also order is 1.
Okay.
And then I look at Cal 1 and 3, where the bromide stays constant, but the
Okay, so that's your table logic. If you had to do ugly algebra, could you do it? Ugly algebra with the rates over the rates.
Yes.
We're going to have to work on that. So that's your quick table logic. You get your rate law to be, or rate equals. So for mean T first. So I think table logic, you guys are getting the hold of pretty quickly. The only reason I wanted to talk about this one is because it talks about something weird to ask for. Oh, no, it didn't ask for anything too weird. So once you get your rate law, you can find your rate law constant by plugging in variables, right? So I always choose trial 1. So if you're ever trying to match up your work with mine, I generally choose trial 1 so we can have some common language to talk about, right? And then this is the weird part. It talks about appearance. So if you're reading it, you're like, what is the rate of appearance of NOVR for trial 4? That's just asking, according to the data table, this gives us, instead of rate of disappearance of a reactant, showing the appearance of a product, but they stoichiometrically are related. So we can actually find the rate of appearance by plugging in these values for trial 4 into our rate law, correct? You with me? Okay. And then, so if I got my rate law and I plugged in my variables, I got the rate for that to be 1.08 times 10 to the second molarity per second. So that's just by plugging in. How would I then find the rate of disappearance for BR2? Yeah, this is appearance of NOVR. This is how this whole data table is spoken of. Because here's our reaction. This is a reactant, this is a reactant, this is the product. So the rate of appearance is how the data is, that's the perspective, is an appearance of a product. But how fast does this reactant disappear as the product is formed? Say again? What do you mean 1 over? What's the relationship between that individual product, the only product, and the reactants asking for, which is BR? 2 to 1. So the rate of formation of that product is what? So the rate of formation of that product is twice as fast as the disappearance of the reactant, yes? This is a 2 to 1 mole ratio. This is where you can relate, once you have the rate, you can relate them to each other and go, this product's forming twice as fast as this reactant is reacting. Got me? So then how do you show that down here? If the rate of, and this information is exactly, is this exactly what was given to you? No, it's not. Let me back up for a second. But if this were saying, okay, the rate of appearance of NOVR is blank, what's the rate of disappearance of BR2, or the rate of disappearance? What you could then do is say, okay, I make, this is NOBR by the way, I make 1 mole of NOBR for every 2 moles of BR2 that I consume or react. So the rate of disappearance would be double that. Oh, no, I'm sorry, I mixed that up. Sorry, 1. I was trying to write the mole ratio last year. So this is 1 mole of, was that 1 mole?
Yes.
Okay, and then that's 2 moles of NOBR, the product. So the rate of disappearance should be half of what the rate of appearance was. Does that make sense, guys? You're using the mole ratio? Okay. I know I'm moving a little bit slow here. Just to make sure everybody catches up with us. And for the last one, you would just plug in variables and go. So here's what I want you guys to try, and then I'm going to head up a couple more examples with graphs. Look at the problem set under, it says differential rate law problem set. It's on page 3. You see page 3. Got like a little diagram with a triangle on it. Well, it's a cyclohexane, cyclopropane, sorry. So I want you guys to do 1 through 6 there, and then I'm going to show you the complex one for the next page. So start wherever you want to. Take 10 minutes maybe right now. Get some of that problem set done, and then I'm going to show you more. Avery.
Get cut off line.
Well, but they're X-ray it standpoint there.
Oh, Castro. Hold on.
The answers are on there as well. type on me. Again, typing up the little answer keys. Sometimes I don't check mine. When I type, so I have to be super pixels for quite a bit.
Okay, so
Yeah, it is weird. Malaria's good. I just typed it wrong, I guess. Never knows that.
so you can plug in, or you can plug that right. So you plug that in for any given month. Just pick one, and it's really easy. So you plug that in, then you divide that. Then you divide that by your basic value, basic portfolio, and just the first times basic value, 2.010 squared. So it's just 2.010 times 2.100 times 2.010, so you calculate it. So when you divide that, it becomes like a huge number because you're just by 0.0000000.
For someone to see,
That's why it's a bit. I can show you. Okay. You have to take. Alright. Yeah. Okay. So when you look at the thing, it says like K is equal to rate over then K is equal to rate. Okay, K is equal to rate over N times N squared. So what you do is you take any given initial rates, if you look at the chart, you take one of the initial rates and you plug that into the rate. So you get 2.5. So it's
Maybe they'll go in there. Maybe they'll want to see what's big.
I don't know how to use it, but the video
I would buy the yeah, if you it's great for the concept. Yes, really good. That was the first it's just because a few people don't want to get to going
Oh yeah, that's usually
Alright, if you're in the middle of a problem, get to a starting point, I'm going to have you guys look at the other problem set, which I think is a little bit more complex. And I thought maybe we could do one or two of those together. And then you guys are doing 1 through 6 on the problems that you've worked on right now. Who's on number 3 at least? Awesome, okay. So finish where you are, and I'm going to choose the one I want to do. Let me look. page 5, AJ, it says using initial concentrations to determine orders of reaction. Let's do a hard one. No. Number 6 is interesting, but you guys, let's do number. What if these are easy at first? Let's do number 4. Number 4, you ready? All right, number 4, and this is on the this is on page 5. You guys have that big table. All right, so let's. I might have to pull this up. Go ahead and start that part without me. I'm gonna pull this up for you. Do number 4 on the other problem set.
Sean and I both just got like a text from Remind from Mr. Davis, I think. It's about emergency weather information. Emergency slash emergency. Huh?
This is a test.
Is it test?
It says this is a test of the Remind 101 apps.
Should I leave?
Why?
I don't know what it is. Guys, it's just a test to make sure it works. Everybody in the school's gonna get it if they've signed up for Remind. Don't worry about it. So they should have started sending us tests.
They're gonna send out. This is another form of communication and inform us about weather. Yeah. It's not snowing right now, but it will. Yes, that's likely going to be another, just a third approach to get us to communicate. Okay.
Yeah.
See, I did. You doesn't matter which one you use. Use the ugly algebra method. It doesn't matter which one you use. And that is. Is it C? I mean, C score. It's supposed to be half. It's supposed to be a half order. What's 1.4? The rate? Are you saying the rate change is 1.4? Okay, but the rate, the factor of the rate change being 1.4 difference means you can't do the table logic because you don't know to what power makes 1.4, so you have to do some logs.
But show it via log, because don't just like put in calculator and guesstimate, you gotta show it via log. Alright, have you guys figured out part of number 4 yet? So who got, give me your attention back, guys. I could just let you work, but I'm trying to make sure I'm guiding you, so work with me. Trials 1 and 2, you got constant, trials 1, 2, B, and C were constant. A was doubled, the rate was quadrupled, so the A has to be second order. You probably were able to find B as well. Did you guys find B's order? What was it? It was 1, right? But you went through your table logic, right? And this is the part where I'm hoping you're like, what do I do here? And so I already got Alvin's asking me that, but I want to make sure the rest of us saw it. I compared trials 1 and 3. I saw A and B were constant, so I was like, I'm going to find C's order. Well, I saw C was doubled. So C was doubled, and the rate here was multiplied by 1.4. Well, that's not really a relationship you can do off the top of your head. So I would then recommend you take that information and go to ugly algebra, which is the rate equals k blah 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 over the rate is equal to k blah blah blah. Cancel the things that are constants, which is k. Plug in your variables for everything else, including what you've solved for already in A and B, and then find what that order is. And then that's going to be where I would force you to show a little work with logs or some of the math setup. So you're going to find you'll do that on a couple of these right here. So, but you guys are responsible. We have 10 minutes left in class. Please do work. You guys are responsible for 1 through 6. I'm going to wait and do lab stuff tomorrow. You're doing the lab comp set that you were working on first, 1 through 6, and then the complex one, number 1 through 6. Get a couple more of those done. And I have 4 textbook questions that I want kind of review, but I'll put this up on the board in 30 seconds.
That was just for knowing, like, it's just minus and plus when the product. So like when you're trying to combine it together, or you just you know the same. It's always your why is that faster about oh wow. Wow, that you only have it's all good. It doesn't
always do like analysis that you're doing?
So I was trying to model like how this is very weird. I was trying to model like an exponential. It's probably going to be constant. I mean, how it could probably be constant. The variable over. Like you can make a linear explanation, but you can't.
Yeah. And then if we do that, we just do explain it once and keep doing it.
I think, yeah, I'd have to see how you did it.
Yeah.
Yeah, I figured out. I was kind of after that first. Did you give this the letter? Did the campus come out, but it was like
So you stole it.
yeah,
Why is it
So speaking of, when you're doing your rates, rate comparisons like this with ugly algebra, always put the larger rate. So I did 3/1, so put the larger rate on top, so you get a number that makes sense, right? Or numbers that maybe you can mathematically solve better for.
I couldn't tell you.
So I got
Like it's UGLY. I'm stressed. It's not us. It's just so funny. Okay. As soon as I was like on the nose, and she was. Okay, I didn't get like square. Oh, that's how much you like multiply. Oh, I got it. So orders can be like fractions and
So
complicated.
Why is there?
Oh, okay.
So why is it on that? So you know how you can go from this to product two? Yeah. It's the same thing. You're trying to find out what your multiple are. So you square it. Because you know that if A is then where do you know? Like you do 2 divided by 1 is 2 is to the x, and what is the square? Like it's 1 point. It's oh, I guess it's 1 point. Never mind. Because 1 squared is 1 half. Yeah, never mind. Yeah, I got it.
Hey, it is clear, for like every vector, it is clear to terminalize the coordinates of the vector. But what you're saying, the minus and plus, you know, we do the cross.
You guys, I'll update real quick, but 136, 136, and the vortex
Yeah, so
Give me range for you, like A, B, C, or D, or F, F or D.
I was like, I ended up with the other one. I put the wrong way. Especially with the 10-point scale, lit. I've been feeling all my classes at least 10 point scale. Except for all time. You feel I just